many important problems related to real crystals can be solved by invoking a mathematical concept known as the reciprocal lattice. Reciprocal lattice exists in an imaginary reciprocal space, just as a real lattice exists in real space. There are definite mathematical relationships between a real lattice and its reciprocal lattice. In fact, there are certain reciprocal relationships which do exist between a real lattice and the corresponding reciprocal lattice. I would like to introduce some simple vector operations at this stage, as because these will be needed when we get deeper into the subject. Well, we all know that a vector has got both a magnitude and a direction. So, in this lecture, a letter written in bold will denote a vector, otherwise it is a scalar quantity. So, magnitude of the vector A can be written in this manner, or it can also be written simply as A. Now, any vector in real space can be resolved into three components along x, y and z. If I, j and k, these are the unit vectors along the directions x, y and z, then a vector A can be resolved into the three components, namely A1i, A2j and A3k. So, a vector A can be written as A1i plus A2j plus A3k, and the magnitude of the vector A is equal to root over A1 square plus A2 square plus A3 square. There are two kinds of vector operations which we normally come across. Suppose A and B are two vectors, and let the angle between the two vectors is theta. So, A dot product the vector B, it is a scalar quantity, and the magnitude of that is the magnitude of A multiplied by magnitude of B multiplied by cosine theta. So, it will be AB cosine theta. On the other hand, there is another product between two vectors. Say for example, this is vector A, this is vector B, and suppose theta is the angle between the two, then A cross B is a particular type of product of these two vectors, and this is equal to a third vector C lying perpendicular to the plane contained by A and B, and its direction can be found out from the right handed screw rule. The magnitude of the vector product A cross B is equal to magnitude of A into magnitude of B multiplied by sin theta, that is AB sin theta. Whereas, the dot product of two vectors is a scalar quantity, the cross product of two vectors is a vector quantity. Now, some simple vector operations will be illustrated here. So, we have written down three vectors in terms of their components in the x, y and z direction. Now, if we make the cross product between the two vectors, so I write these vectors in their components. So, it is axi plus ayj plus azk cross product bxi plus byj plus bzk, and this product can be written simply in a determinant form ijk ax ay az bx by bz, and then it can also be written in this fashion. And similarly, when we make a dot product between two vectors a and b, then we write down the two vectors in the form of their components, and then the product comes out to be ax bx plus ay by plus az bz. Now, this product is also called the inner product. Now, there is an operation between three vectors. Say we first make a cross product of the vectors a and b. So, the cross product will give us another vector. Then we make a dot product of that vector with a third vector c. So, it is a cross b dot c. So, how we are going to do that? Again, there will be a third bracket here which is missing, there will be a third bracket here. Again, we resolve the vectors a, b, c into their components and write it as a dot product, and this is what it comes out to be: ay bz minus az by cx plus az bx minus x bz cy plus ax by minus ay bx cz, and we can write it down in the determinant form. So, you can interchange the columns and write it in this fashion. Now, this product a cross b dot c is also known as what is called the box product, and you can write it down in this fashion: a b c within the third bracket. It can be shown that a cross b dot c is the same as b cross c dot a is the same as c cross a dot b, and in this form it can be written a b c box product equal to b c a box product into c a b box product. So, now we have learned how to find out the cross product between two vectors, how to find out the dot product between two vectors, and how to find out products of the type a cross b dot c. Now, let us go to somewhat more complicated problems. Say for example, we want to find out a cross b cross c. So, b cross c will give us a new vector. So, we have to make a cross product of a with that new vector. Again, the process is write down all those vectors in terms of their components and do all the operations necessary as shown over here. And once we do that, you will find that the product is a dot c b minus a dot b c. So, we have now got a cross b cross c is a dot c b minus a dot b c. Now, if we do it the other way around, if we make a cross product between a and b, and then the new vector with makes a cross product with the vector c, then this is what it will be. It is a dot c b minus b dot c a. So, we have found out a cross b cross c is equal to a dot c b minus a dot b c, and when it is a cross b cross c, then it is a dot c b minus b dot c a. Some few more vector operations, somewhat a little bit more complicated ones. Say for example, we want to find out dot product between a cross b and c cross d. Well, of course, this will be a vector, this will also be a vector. So, how we do it? Say a cross b is equal to the vector phi. So, this product will be phi dot c cross d, and naturally it can be written as a box product phi c d. So, it can be written as phi cross C dot D, and then we know what is phi cross C. It is A cross B cross C dot D, and we already know the value of this product. So, we write it down, and that making a dot product with D, and this will give us a A dot C multiplied by B dot D minus B dot C multiplied by A dot D. So, in a determinant form, it can be written like this. Let us go into another kind of vector operation, say A cross B dot C cross D. Again, we put A cross B is equal to a vector phi, and then proceed in the same manner, and we come across the product in the form of a determinant A dot C, A dot D, B dot C, B dot D. So, if we want to find out the product A cross B cross C cross D, again you can put the cross product of C and D as a new vector P, put it in place here. So, it will be A cross B cross P. So, if you want to bring P on this side, it will minus P cross A cross B, then it will be P dot B A, because we know this product, minus P dot A B. So, it will be finally the box product of C D A B minus box product C D B A. Now, in a similar manner, we can find out the cross product between B cross C and C cross A. Again, we put C cross A equal to vector phi and put it in place here, and if you interchange these two vectors, so phi comes earlier, it will be a minus sign here, phi cross B cross C, and then it will be phi dot C B, because this product we already know, minus phi dot B C, it will be phi dot B C minus phi dot C B, and then we can find out, we can substitute for phi here. So, it will be C cross A dot B C minus C cross A dot C B. So, this will be equal to the box product C A B C minus the box product C A C B. Now, C A B C remains as such, but C A C B, this box product is simply equal to 0. So, it is C A B C, but you see C A B is what? C A B is the box product of C A and B. So, if you look at the unit cell in the real lattice, that really is the volume of the unit cell. So, you can change C A B to V, the volume of the unit cell, to C. Now, of course, it will be a bold C, because this is a vector quantity. So, we have found out if we make dot product between the vectors A cross B and C cross D, it can be written in this form, the determinant form. We also have seen if we do a cross product between the vectors A cross B and C cross D, we can write it in this fashion. And if we do a cross product of B cross C and C cross A, it will be equal to V C. So, these are some of the important products which we should remember, because we may find this from time to time while solving problems using the reciprocal lattice. Now, let us come to the relationship between a real lattice and its reciprocal lattice. Say for example, the unit cell in a real lattice is defined by the vectors A, B and C in the x direction, y direction and z direction respectively. Suppose in an imaginary reciprocal space, we have got another unit cell which is defined by the vectors A star, B star and C star along the x, y and z direction. Now, quite arbitrarily, it has been chosen that this unit cell, if it belongs to a lattice which is reciprocal to this unit cell in the real lattice, then A star will have this kind of relationship with B, A star, B star and C star, the lattice parameters of the unit cell of the reciprocal lattice will have this kind of relationship with A, B, C, the vectors which define the unit cell in the real lattice. And what is this relationship? A star is equal to B cross C by V, where V is the volume of the unit cell in the real lattice. B star is equal to C cross A by V, where V is the volume of the unit cell in the real lattice, and it will be C star, I am sorry, C star is equal to A cross B by V, where volume V is the volume of the unit cell in the real lattice. So, it seems to be there seems to be some madness into this whole scheme. Why should A star be equal to B cross C by V, B star should be C cross A by V, and C star should be A cross B by V? Well, there is some method in this madness, as we will readily find out. So, you see, we should think about the two things together: a real lattice existing in the real space and a reciprocal lattice existing in an imaginary reciprocal space. So, this is the unit cell of the real lattice, this is the unit cell of the reciprocal lattice, this is reciprocal to this. Now, we have said quite arbitrarily that the lattice parameters of the unit cell in the real lattice A, B, C, and the lattice parameters of the unit cell in the corresponding reciprocal lattice A star, B star and C star are related in this fashion. A star equal to B cross C by V, B star is equal to C cross A by V, C star, it is not A star here, C star is equal to A cross B by V. Now, we will readily see why such relationships have been assumed. Let us suppose that this is a unit cell in the real lattice. This is a unit cell in the real lattice. This is the A vector, B vector and C vector. So, A, B and C define the unit cell in the real lattice. Now, we have assumed that C star is equal to A cross B by V. So, if this is the unit cell of a cubic lattice, and since C star is equal to A cross B by V, C star will be pointing in a direction perpendicular to the plane contained by A and B. So, as a result, the C star vector will also be along the C vector. So, C star, the magnitude is equal to A cross B by V, and what is A cross B? It is actually the parallelogram, area of the parallelogram A, B, C, D. So, this area of the parallelogram is A cross B, and what is V? V is the area of the parallelogram A, B, C, D multiplied by the height of the cell. So, the whole volume of the unit cell is this parallelogram area of this parallelogram multiplied by the height. So, we can write it down is equal to 1 by AP. So, this is the point P which has not been shown, or AP is the same as C. So, we can write it down, this is equal to 1 by the magnitude of the vector C. But what is the vector C, this length C after all? You see, C is nothing but the interplanar distance of the 0, 0, 1 planes. You see, this is the 0, 0, 1 plane and bottom plane is 0, 0, bar 1 planes. So, these are parallel planes and the interplanar distance is given by the magnitude of this vector C. So, we find that the magnitude of the vector C star is actually the reciprocal of the 0 of the interplanar distance of the 1 planes in the real lattice. In a similar way, we can find out the magnitude of the vector A star is equal to the reciprocal of the interplanar distance of the 1 0 planes. This is the 1 0 plane, this is the back side is the bar 1 0 plane. So, this is the interplanar distance. So, magnitude of S star is equal to the reciprocal of the interplanar distance between the 1 0 planes. Then magnitude of B star is equal to the reciprocal of the interplanar distance of the 0 1 0 planes. These are the 0 1 0 planes, and C star, as we found out earlier, is equal, the magnitude of C star is equal to the reciprocal of the interplanar distance of the 0 0 1 type planes. So, if we plot a unit cell in the real lattice, suppose this is a cubic unit cell in the real lattice, and say the lattice parameter is 2 angstrom, then if you take a plan view of this unit cell, say this plane here, as we all know, is a 1 1 0 plane, and this right hand side plane here is 1 0 0 plane. So, if we look from the top, the plan view, then this is what the the trace of the 1 1 0 plane look like, and this will be what the 1 0 0 plane look like. Now, correspondingly, if we have the unit cell in the reciprocal lattice, it can be easily found out that the lattice parameter will be equal to 0.5 angstrom. We will see why it is so later. And if we take a plan view, then if you join this point to that point, this is this direction, and what is this? This is the direction 1 1 0 in the reciprocal lattice. And what about this direction here? In the plan view, this is this direction, and this is nothing but the 1 0 0 direction in the reciprocal space. So, what we find, the 1 1 0 direction in the reciprocal space is perpendicular to the 1 1 0 plane in the real space, and 1 0 0 direction in the reciprocal space is perpendicular to 1 0 0 plane in the real space. So, some interrelationships can be already found out between a real lattice and its reciprocal lattice. Now, there are 3 general relations that can be proved between real and reciprocal lattices. Now, the first relationship is, if we draw a vector sigma star HKL from the origin of the reciprocal lattice to a point HKL in it, then that vector can be simply written down into its components H S star plus K B star plus L C star. Please remember, A star, B star and C star should be bold, and these are vectors. So, the vector sigma star HKL in its 3 components are H S star plus K B star plus L C star. So, this vector in the reciprocal lattice will be perpendicular to the HKL plane in the real lattice. In the previous diagram, we have already seen such a thing. So, the first relationship that exists between a real and a reciprocal lattice are any vector sigma star HKL in the reciprocal lattice starting from the origin of the reciprocal lattice to a point HKL in it will be perpendicular to the HKL plane in the real lattice. Not only that, the second relationship is the magnitude of the vector sigma star HKL will be equal to the reciprocal of the interplanar distance of the HKL planes. This is the second relationship. We can write it simply as sigma star HKL is equal to 1 by d HKL. And the third relationship is that V star, volume of the unit cell in the reciprocal lattice, is equal to reciprocal of the volume of the unit cell in the real lattice. So, these three relationships we are going to prove now. Say for example, we take any kind of unit cell in the real lattice. Say we have a real lattice, and we consider this is the x axis, this is the y axis, and this is the z axis, and say the lattice parameters of the unit cell are simply a, b and c. Now, if we plot a plane a, b, c in this real lattice, and if it is an HKL plane, then what will happen? This intercept will be equal to a by h, this intercept will be equal to b by k, this intercept will be equal to c by l. Okay? We know that if you have a plane HKL and if it cuts the x, y and z axis along at the points a, b and c, in that case the intercepts will be a by h along x, b by k along y and c by l along z. Now, suppose through the point O we draw a straight line parallel to the vector sigma star HKL in the reciprocal space. So, what essentially we are doing? We have got a real space, and at the same time we have got a reciprocal space. So, we have got a situation like this. These are the x, y and z axis, and suppose we have got a situation that we have got an HKL plane over there. So, if it is an HKL plane and if A, B and C are the lattice parameters, then obviously from the origin this distance will be equal to A by h. So, this distance will be equal to A by h Similarly, this distance over here from here will be equal to b by k and this distance over here will be equal to c by l. Okay. Then only this will be an HKL plane. So, if we consider this as an HKL plane in the real lattice, and if A, B, C are the lattice parameters along x, y and z, then the intercept of the HKL plane on the x axis will be A by h, intercept on the y axis will be b by k, intercept on the z axis will be c by L. Now, side by side we can construct a reciprocal space, an imaginary space, and suppose we have got the origin of the reciprocal space denoted by the point O star, just as the origin in case of the real space is O. Now, say this is a point HKL, this is a point HKL in the reciprocal space. This is a point HKL reciprocal space. So, if from the origin of the reciprocal space we draw a line to HKL. So, if we draw a line to HKL, then what is this vector going to be? We call this vector as sigma star HKL. We name this vector sigma star HKL. So, naturally any vector, it can be resolved into 3 components. So, in the reciprocal lattice you can resolve the vector along A star, along B star and along C star. So, we can write down this as a vector H S star, H S star plus K B star plus L C star. So, now what we are going to prove? We are going to prove that this vector in the reciprocal lattice is going to be perpendicular to the HKL plane in the real lattice. So, what we do over here, through the origin of the reciprocal of the real lattice, we draw a line parallel to the sigma star HKL line. So, what we do essentially is from the origin of the real lattice, we draw a line parallel to sigma star HKL in the reciprocal lattice. So, suppose we do that, and suppose it cuts the HKL plane at the point P. Suppose it cuts the HKL plane at the point P. So, we have a situation that we have a vector sigma star HKL in the reciprocal space, which is equal to H S star plus K B star plus L C star, and in the real lattice we have got an HKL plane. We draw a line from the origin of the real lattice parallel to a vector parallel to the sigma star HKL vector in the reciprocal lattice, and suppose this cuts the HKL plane at the point P. Now, since OA is equal to A by H, so we can write down, since OA is A by H, OB is B by K, OC is C by L. So, in vectorial notation we can write OA is equal to A by H, A being a vector, OB vector is equal to B by K, B being a vector, OC is equal to C by L, C being a vector. So, AB vector is equal to OB minus OA, so it will be equal to B by K minus A by H, and SC will be equal to OC minus OA equal to C by L minus A by H. Now, if we take a dot product between the sigma star HKL vector and the AB vector, we can write down into the components of sigma star HKL, the component, in the component form, we can write down sigma star HKL is equal to H S star plus K B star plus L C star, and it's a dot product B by K minus A by H. Now, if we do the dot product, it becomes equal to 0. And what does that indicate? If the dot product is 0, that shows that sigma star HKL vector is perpendicular to the vector AB. In a similar manner, if we do the dot product between sigma star HKL vector and the vector AC, we can again write down in its component form H star plus KB star plus LC star dot C by L minus A by H. It is again becoming 0. So, that means sigma star HKL vector is perpendicular to AC also. So, we see that sigma star HKL vector is perpendicular to the vector AB as well as to the vector AC, or in other words sigma star HKL vector is perpendicular to the plane ABC or the plane HKL. So, the first relationship that we mentioned earlier is proved. Now, let us go to the second relationship. You see, this length, this is the vector parallel to the sigma star HKL vector. So, if we find out this length OP, how much is OP? It is erroneously written here as 1 by DHKL, actually it will be simply DHKL. You see, OP is nothing but the interplanar distance of HKL type of planes. So, this is an HKL type of plane, here there will be a parallel HKL type of plane. So, the distance between the two, this OP is actually the interplanar distance of HKL type of planes. So, the magnitude of OP is simply DHKL, not 1 by DHKL. This is wrong, you know. So, there should be a correction. So, magnitude of OP is simply equal to DHKL. Now, let us consider a unit vector S along OP. So, if we say there is a unit vector along OP, what it means? Unit vector means, after all, this is the sigma star HKL vector. This vector is parallel to and equal to the sigma star HKL vector. So, unit vector along this direction is nothing but the sigma star HKL vector divided by the magnitude of the vector. So, we will be using these two relationships. Please remember that the magnitude of OP is simply DHKL and not what is written here. Now, let this angle between OP vector and OA vector be equal to theta. Now, what is OP vector? OP vector, you can write it as OA vector into cosine theta. OP vector is nothing but OA vector to cosine theta, you know, from this right angle triangle. So, it is equal to, we can also write it as OA vector dot S, the unit vector along OP, it is the same thing. So, how much is this? OA is the vector A by H, dot product, what is S? The unit vector along sigma star HKL. So, it is sigma star HKL divided by magnitude of sigma star HKL, and then it is equal to A dot, you know, now we write down the sigma star HKL vector into its components. So, it is HS star plus KB star plus LC star, and in the denominator we have H and the magnitude of sigma star HKL only. So, you know, this sigma should be in lower case, you see, it is not a vector as we can see over here. So, this is equal to H divided by H, the magnitude of sigma star HKL, that means it is equal to 1 by magnitude of sigma star HKL. But already have seen that OP is DHKL. So, OP is already we have found out that is DHKL, and at the same time what we find, OP is 1 upon the magnitude of sigma star HKL. So, DHKL is equal to 1 by magnitude of sigma star HKL. So, we can write the magnitude of the vector sigma star HKL is equal to 1 upon DHKL. So, this is what we wanted to prove as the second relationship between a real lattice and a reciprocal lattice. Now comes the third relationship between a real lattice and a unit cell in the real lattice and unit cell in the corresponding reciprocal lattice. Say this is the unit cell in the real lattice, its volume is V, and V can be written as the vectors A cross B and dot product between this and the vector c. Similarly, if this is the unit cell in the reciprocal lattice, this is the corresponding unit cell in the reciprocal lattice, then it is defined by the vectors A star, B star and C star. So, the volume of the unit cell V star can be written as the cross product A star cross B star and dot product of this with the vector C star. So, easily we can write the volume V star is the box product of the three vectors A star, B star, C star. So, this is equal to A star cross B star dot C star. Now, we know that A star is equal to B cross C by V, and B star is C cross A by V, and C star is A cross B by V. So, we have got 1 upon V cube, and this product we know is V c minus 0 dot A cross B, and this is 1 by V cube V c dot A cross B, and we know that C dot A cross B is again V. So, it will be 1 by V cube multiplied by V into V, that means it becomes 1 by V. So, the volume of the unit cell in the reciprocal lattice is the reciprocal of the volume of the unit cell in the real lattice. So, these are three very important relationships which exist between a reciprocal lattice and a corresponding real lattice, or between a real lattice and the corresponding reciprocal lattice. So, we have proved that a vector sigma star HKL in the reciprocal lattice is perpendicular to the plane HKL in the real lattice. The magnitude of the vector sigma star HKL is the reciprocal of the interplanar distance of the HKL planes, and the volume of the unit cell in the reciprocal lattice is reciprocal of the volume of the unit cell in the real lattice. We are now going to prove another very important relationship using the reciprocal lattice concept, and this is the concept of a zone of planes and the zone axis. Now, suppose this is a cubic unit cell in the real lattice. Now, if we look at the top plane over here, we know that the top plane is the 0, 0, 1 plane. If we take the right hand side plane here, this is the 0, 1, 0 plane. If we talk about the bottom plane here, it will be the 0, 0, bar 1 plane. And if we look at the left hand side plane here, it will be the 0, bar 1, 0 plane. So, the top plane, the right hand side plane, the bottom plane and the left hand side plane, each one of them is parallel to an axis perpendicular to the plane of the board. That means, what is this direction? This direction in the cubic unit cell is nothing but the 1, 0, 0 direction. This is the 1, 0, 0 direction. 1, 0, 0 direction is perpendicular to the 1, 0, 0 plane. So, what we find that these 4 planes, each one of them is such that it is parallel to the direction 1, 0, 0, the same direction. In such a case, we say that these 4 planes, they belong to one zone. we say that these 4 planes belong to one zone, and this direction with which they are parallel to is known as the zone axis. So, this is a very important relationship in crystallography. Similarly, if we look at the front plane, the right hand side plane, the back plane and the left hand side plane, all 4 planes are parallel to this axis, which is the 0, 0, 1 direction. So, this plane, the bottom plane and the front plane, right hand side plane, back plane and left hand side plane, they are all parallel to the 0, 0, 1 direction. So, those 4 planes also form a zone with this direction of the zone axis. Now, we are going to prove a relationship and find out what relationship exists between a zone and zone axis, and if a given zone axis is given, say if a zone axis is designated as UVW, using the relationship which we are going to prove, we can easily find out whether a plane HKL will belong to a zone for which this is the zone axis. Now, let us see how to proceed with this. Say for example, we have a plane HKL plane in the real lattice. This is the line on the plane. Say this is a direction perpendicular to the plane, and I have written sigma star HKL. This is very clear because we have already seen that if we have an HKL plane in the real lattice, then the vector sigma star HKL in the reciprocal lattice is going to be perpendicular to this plane. Let us inscribe a line called I UVW. So, this point is the UVW point. So, this vector I UVW connects this point, the origin, to the point UVW in the real lattice. Now, this line and this line are say coplanar. Say, suppose this angle between I UVW and AB is rho. In that case, this angle between I UVW and sigma star HKL will be 90° minus rho. So, now we can write down I UVW vector. It is in the real space. It is equal to UA plus VB plus WC. So, if we make a dot product of I UVW and sigma star HKL, then it will be I UVW magnitude of that, sigma star HKL magnitude of that into cosine of 90° minus rho. So, it will be magnitude of I UVW into sine rho, and since this is sigma star HKL is equal to 1 by d HKL, we can write it in this fashion. It will be I UVW sine rho by d HKL. So, again you know that sigma star HKL, the magnitude is nothing but its magnitude is equal to 1 by d HKL. So, I have written instead of sigma star HKL, I have written 1 by d HKL. Now, if you write down I UVW into its component vectors, it will be UA plus VB plus WC, and if we write down the sigma star HKL vector in the reciprocal lattice into its components, it will be HS star plus KB star plus LC star. So, if we make a dot product between these two, it can be easily seen that the dot product will be HU plus KV plus LW. So, we see that the dot product between these two vectors is equal to HU plus KV plus LW, and again the dot product between these two vectors is equal to I UVW sine rho by d HKL. So, we equate these two. If rho is equal to 0, sine rho will be automatically 0 and HU plus KV plus LW will be 0. You see, rho 0 means that this plane HKL plane will be parallel to the direction I UVW. So, the HKL plane and the UVW direction will be parallel, and the condition is HU plus KV plus LW is equal to 0. So, if HKL plane belongs to a zone where UVW is the zone axis, then the relationship must be HU plus KV plus LW is equal to 0. Otherwise, this plane will not belong to the zone UVW. So, using this relationship, we can find out quite a few things. Say for example, we have got two planes HKL and H prime K prime L prime belonging to the same zone, for which the zone axis is UVW. So, using that relationship, the zonal relationship, we can write down HU plus KV plus LW is equal to 0, H prime U plus K prime V plus L prime W is equal to 0. And so, by cross multiplication, we can find out U divided by this is equal to V divided by this is equal to W divided by this. So, U is to V is to W is equal to this quantity is to this quantity is to this quantity, and these are known quantities because I know I have been given those two planes. So, I can easily find out what UVW are going to be. So, you see that using the zonal relationship, we can find out whether a particular plane will belong to a particular zone having a particular zone axis. Not only that, if we know more than one planes which belong to a zone, then using the zonal relationship, we can also find out what should be the zone axis.